You already know the sun is going to die. You have probably seen the videos. The sun swells. It turns red. It swallows Mercury. It swallows Venus. And somewhere in that fire, what is left of Earth drifts through the outer layers of a star that has decided, after billions of years, that it is finally done with us. That happens in about 5 billion years. It is not what you should be worried about. The sun is going to kill you, your children, every species you have ever loved, every city you have ever stood in. But it is not going to wait 5 billion years to do it. The deadline is closer than that, much closer. And the first stages of the execution are happening right now, in the light hitting your face. There are 3 ways the sun ends us. Only one of them is the red giant. The other 2 are already on the calendar. One of them rehearsed 12 months ago, in May of 2024, when a storm came within hours of taking down the modern world. The other one ends complex life on Earth in roughly 1 billion years, long before the sun ever swells, long before it ever turns red. 5 billion years is the headline. It is not the deadline. This is what we actually know about how the sun kills its planet, not the cinematic version, the real one. 5 billion years is the number you have been given. It is the time, roughly, until the sun exhausts the hydrogen in its core, swells into a red giant, and begins to consume the inner solar system. 5 billion years is the number that lets you sleep, because 5 billion years is forever. 5 billion years is so far away it stops feeling real. 5 billion years is a problem for a species we cannot even imagine, if any species is here at all. Here is the thing. By the time the sun is large enough to threaten Earth physically, there has been nothing alive on this planet for nearly 4 billion years. The number you should have been given is 1 billion. In about 1 billion years from now, current best estimate around 1.1 billion, though some models push it as far as 1.4. The sun will be approximately 10% brighter than it is today. That sounds small. It is not small. A 10% increase in solar luminosity is more than enough to push Earth's average surface temperature past the point where liquid water can stably exist at the equator. The oceans do not boil away on day one. They evaporate slowly over tens of millions of years into a thick water vapor atmosphere. Water vapor is itself a powerful greenhouse gas, so the warming runs away from itself. Once you start, you do not stop. The sun keeps brightening. The vapor keeps trapping more heat. The oceans keep cooking off. Eventually the planet's water inventory rises high enough into the upper atmosphere that ultraviolet light from the sun breaks the molecules apart, hydrogen by hydrogen. The light hydrogen escapes to space. The water is gone forever. Earth has just become Venus. Complex life, animals, plants, anything that drinks water and breathes air, is gone hundreds of millions of years before that. Single-celled extremophils cling on for a while. They cling on in the deep crust, in pockets of brine, in places we still cannot reach with submersibles. The last living thing on Earth dies somewhere between 2.5 and 2.8 billion years from now. Not in 5 billion, in 2.8 billion. And complex life, anything you would recognize as alive, is over in 40,000 human generations from now. That is the deadline. The sun does not need to swell up and devour us. It does not need to turn red. It does not need to do anything dramatic. It just has to keep doing what it is doing right now, very slowly, getting 1% brighter every 100 million years. That is enough. The sun is killing us already. The atoms in your eyes today are catching photons from a star that is fractionally brighter than the one your great-great-great-grandmother saw. In about 1,000 human generations, the difference becomes lethal. There is a process buried inside that timeline that nobody talks about, and it is the actual murder weapon. It is called silicate weathering, and it is the reason the Earth has been habitable for the last 4 billion years. Most of the carbon dioxide that ever existed on Earth is not in the atmosphere. It is locked up in rocks. Specifically, it is locked up in carbonate rocks, limestone, chalk, marble, formed when atmospheric CO2 dissolves in rainwater, runs over silicate minerals on the surface, reacts with them chemically, and washes the resulting carbonate ions into the oceans. There, marine organisms incorporate it into their shells. The shells eventually become the floor of the sea. The sea floor eventually becomes rock. The rock is the carbon's grave. This is silicate weathering. It is a thermostat. The hotter the planet, the faster the rain falls, the faster the rock weathers, the faster CO2 gets dragged out of the air and buried. Over geological time, the cycle has kept Earth's average temperature in the narrow band where water is liquid, even as the sun has steadily grown brighter for 4 billion years. The thermostat has a ceiling. As the sun continues to brighten, the planet keeps trying to cool itself by dragging more CO2 into the rocks. Eventually, atmospheric CO2 drops below the level that plants need to photosynthesize. Plants using the older C3 photosynthesis pathway, like trees and most crops, die first, somewhere between 600 and 800 million years from now. C4 plants, the ones that evolved more efficient carbon capture biology, like maize and sugarcane and most tropical grasses, hold on a little longer, maybe another 100 to 200 million years. After that, you have a planet with oceans, oxygen, but nothing that breathes or grows. Then the silicate weathering thermostat finally gives up. The sun is too bright. The greenhouse runs away. The oceans go. It is the cleanest extinction event in the planet's history. Nothing about it is dramatic in cosmic terms. The sun does not have to do anything new. It just has to keep doing what it does. So when somebody tells you the sun will eat Earth in 5 billion years, they are technically correct. They are also lying by omission. The sun does not need to eat us. By the time it gets around to it, there is nothing left to eat. Now, here is the part that is harder to dismiss. The 1 billion year deadline is far enough away that your brain refuses to engage with it. That is fair. There is a second death, much closer, that you can actually feel. It has rehearsed twice in the last 200 years. It nearly hit last spring. It is called a coronal mass ejection, CME. It is the sun, at random intervals, throwing out a billion-ton chunk of magnetized plasma in our general direction at several million kilometers per hour. It is the sun's normal weather. We just happen to live in its splash zone. Most CMEs miss us. The ones that hit us mostly do nothing. The ones that hit us hard enough do this. On the 1st of September 1859, a British astronomer named Richard Carrington was sketching sunspots in his observatory in Surrey when he saw two patches of intense white light flare on the sun's surface. He was looking for the first time in human history at a solar flare. About 17 hours later, the CME associated with that flare arrived at Earth. Telegraph systems across the world failed. In some offices, the wires sparked. In Boston and Philadelphia, telegraph operators reported their equipment continued to transmit messages after being disconnected from its batteries, powered entirely by the geomagnetic current induced in the lines. Aurorae were visible as far south as Cuba, the Bahamas, and Hawaii. People in the Rocky Mountains woke up at 1 in the morning convinced it was sunrise. That was 1859. The technological infrastructure of the entire planet was a few thousand miles of telegraph wire. The Carrington event was an inconvenience. In 1989, a much smaller CME, perhaps a tenth the size of the Carrington event, struck Earth. The Hydro-Quebec power grid collapsed in 90 seconds. 6 million people lost electricity. Transformers melted in New Jersey. The aurora was visible from the Caribbean. Insurance estimates put the damage at hundreds of millions of dollars in 1989 currency. That was a tenth of a Carrington. In May of 2024, the sun produced a sequence of X-class flares from an active region designated 36664, one of the largest sunspot groups in 2 decades. The associated CMEs arrived at Earth on the 10th and 11th of May. The geomagnetic storm reached G5, the highest level. Aurorae were visible from Mexico, from Spain, from Australia. SpaceX reported degraded performance in Starlink satellites. Several spacecraft executed emergency safe mode maneuvers. Tractors with GPS-guided auto-steer drifted off course in the middle of fields. Power grid operators across North America were on emergency standby. This was the largest geomagnetic storm since 2003. The current generation of grid infrastructure had never been tested at this level. We were, by most engineering estimates, close to but not at Carrington equivalent intensity. Maybe a third, maybe half. We got lucky. A true Carrington-class event hitting modern infrastructure is not an inconvenience. The most widely cited risk study, published in 2013 by Lloyds of London and Atmospheric and Environmental Research, estimated that a Carrington-equivalent storm hitting the United States today would cause between $0.6 and $2.6 trillion in economic damage in the first year. 8 million people, 20 million people, 40 million people. Without electricity, without water pumps, without refrigeration, without medical supply chains, not for hours, for months. The transformers required to replace what would burn out take 18 months to manufacture, and most of the production lines are in Asia. The Sun has produced events at least as large as the Carrington in the last 2,000 years. We know this from carbon-14 spikes preserved in tree rings, particularly the 774 AD Miyake event, which appears to have been roughly 10 times larger than Carrington. We just had no electricity then, so nobody noticed. Best current estimate of the recurrence rate for Carrington-class events is somewhere between 1 in 100 years and 1 in 200 years. We are 165 years past the last one. The arithmetic is not subtle. The Sun does not see Earth. It has no awareness that there is a planet here, populated by 8 billion small mammals, threading carbon and electricity through every continent. The Sun is a thermonuclear fusion reactor 1.4 million kilometers wide, fusing 600 million tons of hydrogen into helium every single second. It has been doing that for 4.6 billion years. What you experience as sunlight on your skin began as a gamma-ray photon deep in the Sun's core around 100,000 years ago. That photon spent the entire intervening time bouncing through the dense plasma of the radiative zone, about 1.4 light seconds of distance covered in roughly 1,000 centuries of random walk, before it broke into the convective layer, surfed up to the photosphere, and finally launched into space. 8 minutes and 20 seconds later, it hit your retina. The Sun's only relationship with you is that it once, 100,000 years ago, produced a photon, and that photon eventually arrived, multiplied by every photon hitting the Earth-facing hemisphere every moment. That is the Sun's only message to you. There is nothing aimed. That is what makes the Carrington-class flare interesting. It is not malice. It is not punishment. It is geometry. Every several decades to centuries, the Sun does something that, by pure statistical chance, was going to do anyway. And by another roll of the dice, the burst happens to be pointed at Earth. This is the death that does not care who you are. A geomagnetic superstorm strips power from a hospital in Mumbai and a billionaire's bunker in Wyoming with exactly the same indifference. The grid does not negotiate. The transformer does not check your bank balance before it explodes. The Starlink terminal connecting your luxury yacht and the Starlink terminal connecting a refugee camp both go dark at the same instant. This is one of the strange comforts of cosmic threats. They are the only kind of catastrophe in the modern world that genuinely does not care about your money. Asteroid impacts, gamma-ray bursts, supernovae, coronal mass ejections. The Sun is, by accident, the largest egalitarian force in the universe. The 398 most liked comment under one of the top videos about the Sun's death online says, more or less, "The part that comforts me is the elites won't survive either." The comment is correct. The Greeks knew the Sun was dangerous. They did not know about fusion or coronal or magnetic field lines, but they understood, in the way that mythologies understand, that something this powerful was something you respected by keeping your distance. Icarus was the son of Daedalus, the inventor. They were imprisoned by King Minos in Crete, and Daedalus built wings of feathers and wax for both of them to escape. He warned his son, "Do not fly too high, the sun will melt the wax. Do not fly too low, the sea will soak the feathers." Icarus, like every teenager in every culture in every century, did not listen. He flew too close to the sun. The wax melted, the feathers fell. He drowned. Phaeton was the son of Helios, the sun god himself. He demanded as a teenager to drive the chariot of the sun across the sky. Helios warned him, "The horses are wild, the path is narrow, the chariot will scorch the earth if you stray." Phaeton again did not listen. He took the reins. He lost control. The chariot swung too close to the earth. The earth caught fire. Zeus killed him with a thunderbolt before he could finish the job. Both stories are about the same thing. The sun is a power you cannot bargain with. Get too close, and you die. Get too far, and you also die. There is a narrow corridor, the habitable zone, modern astronomy calls it, and humanity is at the center of it because of luck and weathered rock, and not because of any pact between us and the star. When Carl Sagan said, "We are made of star stuff," he meant it literally. The calcium in your bones, the iron in your blood, the carbon in every cell of you, the oxygen you're breathing right now. Almost every atom of you that is not hydrogen was forged in the core of an ancient star, billions of years ago blown into the interstellar medium, drifted for an unimaginable time, and eventually condensed into the molecular cloud that became our solar system, and eventually you. The sun did not make you. The sun is your inheritance from a previous star. When the sun dies, the star that made you will not be the one that ends you. The sun is just the one in the room with you right now. This is the one you've been waiting for. Roughly 5.4 billion years from now, by current best stellar evolution models, the hydrogen in the sun's core will be exhausted. The fusion that has held the star up against its own gravity for almost 10 billion years stops. The core, no longer producing radiation pressure, begins to collapse under its own weight. The collapse heats the core back up. Hydrogen fusion now ignites in a thin shell around the dead helium core. Because the shell is denser and hotter than the original core, it fuses faster, much faster. The sun begins producing more energy than it ever did during its main sequence life. The outer layers, with nothing to balance against, inflate. The sun swells. Over a few 100 million years, the radius of the sun grows from roughly 700,000 kilometers to over 200 million kilometers. The surface temperature drops from around 5,800 Kelvin to around 3,500 Kelvin. The color shifts from yellow-white toward orange-red. This is the red giant phase. Mercury orbits at 58 million kilometers from the sun. As the sun expands past 58 million kilometers, it engulfs Mercury. The planet is vaporized in roughly a year. The thin upper atmosphere of the red giant is hot enough to melt rock, dense enough to apply aerodynamic drag, and Mercury, a planet smaller than our moon, gives up its structural integrity within a few orbits. Venus orbits at 108 million kilometers. The sun reaches it next. Same fate. Faster even, because Venus is closer to the surface. Earth orbits at 150 million kilometers. This is where it gets interesting. There are two competing simulations of what happens to Earth, and the answer is genuinely not settled. As the sun loses mass during the red giant phase, and it loses a lot, perhaps a third of its total mass, its gravitational pull on Earth weakens. Earth's orbit migrates outward, like a satellite released from a tether. If the sun loses mass quickly enough, Earth can migrate fast enough to stay just ahead of the expanding photosphere. If the sun expands faster than Earth migrates, it engulfs us. The best current models, including work published by Schroeder and Conan Smith in 2008 and refined since, lean toward engulfment. Earth almost certainly does not escape. The tidal drag from the sun's outer atmosphere slows Earth's orbit enough that the planet spirals in and is consumed within a few hundred years of entering the photosphere. So, in roughly 5.4 billion years, what is left of Earth, its iron core, its silicate mantle, the scoured rock that used to be its surface, the ghost of every continent, falls into the body of a dying star and is vaporized. There will be nobody here to see it. There has been nobody here for over 4 billion years, the site of every human war, every cathedral, every poem, every kiss, gone into the gas of a sun in its final inflation, undetectable, unrecorded. That is the cinematic moment. That is the part everyone makes videos about. It is real. It is also, in a way, the first two deaths were not, completely abstract. The red giant phase does not last. The sun, having burned through helium in its core to produce carbon and oxygen, is not massive enough to ignite carbon fusion. The helium runs out. The outer layers, no longer being inflated by furious shell burning, are blown gently away into space. The sun sheds nearly half its remaining mass over a few tens of thousands of years. What is left is the core, about the size of Earth, about half the mass of the original sun, white hot, packed so densely that a teaspoon of it would weigh several tons. This is a white dwarf. The outer layers, expelled into space, glow for a brief cosmic moment, perhaps 10,000 years, as a planetary nebula. The Helix Nebula in Aquarius and the Ring Nebula in Lyra are what our sun, in 5 billion years, is going to look like for 10,000 years. Beautiful, brief, then gone. The white dwarf at the center cools. It has no fusion to sustain it. It radiates its leftover heat into space. Over hundreds of billions of years it dims, after about 1 trillion years, a number with no human reference, but bear with it, the white dwarf is cool enough that its interior begins to crystallize. Carbon, oxygen, crystallized. From the inside out, in the highest pressure cores of these dead stars, the elements fall into ordered atomic lattices. Diamond, the sun, in roughly 1 trillion years, becomes a sphere of crystallized carbon and oxygen, slowly fading toward black, the size of Earth, the mass of a star, glowing at a temperature near absolute zero. A diamond, the size of a planet, the mass of a sun, drifting through a galaxy that by then has merged with Andromeda, used up most of its star-forming gas, and slid into the slow dim end of what astronomers call the stelliferous era. That is the corpse of our star. There is more. Stars have been forming in the universe for about 13 billion years, since the first hydrogen clouds collapsed after the Big Bang. Star formation cannot continue forever, because the universe is finite, and the gas keeps getting locked up in dead remnants. White dwarfs, neutron stars, black holes, that do not give it back. The current best estimates suggest that the last stars in the observable universe will finish forming around 100 trillion years from now. After that, no new starlight. The remaining stars, mostly small red dwarfs that burn very slowly, persist for another 1 trillion years or so. Then they go out. After about 10 to the 14 years, a number that means 100 trillion, the cosmos is dark. The only sources of light are the cooling white dwarfs, the neutron stars still spinning, and the occasional infall of matter into black holes. After about 10 to the 40 years, a 1 followed by 40 zeros, the protons that make up most of the matter in the universe begin to decay, if grand unified theories of physics are correct. This includes the matter that used to be your body, dispersed for unimaginable time across the cooling cosmos. Each proton has a half-life roughly 10 to the 34 times the current age of the universe. Slowly, atom by atom, the matter of the universe ceases to exist as ordinary matter. After about 10 to the 67 years, the smaller black holes have evaporated by Hawking radiation. After 10 to the 100, a 1 followed by 100 zeros, a number that has no name, the supermassive black holes are gone, including the one at the center of our galaxy, including every other supermassive black hole in every other galaxy we can see. There is nothing left except a thin bath of photons and neutrinos in a universe expanded so far that nothing will ever interact with anything else, ever again. This is what cosmologists call the heat death. It is the deepest known prediction of physics. Nothing happens and keeps not happening forever. The sun's death on this scale is unremarkable. It is the death of 1/1000th of the universe's stars, somewhere in the 1% of cosmic history, in a galaxy that itself has another 10 billion years to live before it merges with its neighbour. The sun is small. The sun is brief. The sun is, in cosmic accounting, a single quiet candle in a corridor of trillions, and ours, the planet that happened to circle it, is a footnote on a footnote. That is the actual perspective. That is the genuine scale. People ask the obvious question: can humanity outlive any of this? It depends on which death. The Carrington-class storm is survivable. The infrastructure damage is real, but a 12 to 24 month rebuild, painful, costly, killing a lot of people in the gap, is recoverable. We have known about the threat since 1859. The protection technology exists: surge-protected transformers, isolated grid segments, hardened electronics. Most of it is unfunded because the recurrence interval is longer than political memory. If you wanted a project that would tangibly preserve human civilization, that is the one. It is also the only one of the 3 deaths a single generation can act on. The 1 billion year biosphere shutdown is harder. By the time it arrives, our descendants, if there are any, have had 1 billion years to figure something out. 1 billion years is 20 times longer than the entire age of mammals. If a species can persist long enough to remain technological, the engineering problem of moving Earth's orbit outward or migrating to a different planetary system is solvable. It is not solvable for us. It is potentially solvable for whatever we become. The proposal goes back to Freeman Dyson. Build a sphere, a swarm of solar collectors, really, the misnamed Dyson sphere, around the sun, harvesting most of its energy. Use that energy to drive interstellar travel. Leave. Pick a younger, smaller, redder star, there are many, and most of them will outlive the Sun by a factor of 100 or more and settle there. The smallest M-dwarf stars burn for 10 trillion years. If our descendants ever made it to Proxima Centauri or one of the other red dwarfs within a few light years, they would have, in principle, 10,000 times as long as the Sun is going to give them. The red giant phase is, in the end, unsurvivable in this solar system. There is no engineering that keeps a planet at 1 AU from a star with a 200 million kilometre radius. You leave or you die. Probably both. The heat death of the universe is unsurvivable by definition. Some cosmologists, Freeman Dyson again among them, have speculated about whether some form of information processing, call it thought, could be slowed down asymptotically, using less and less energy in each successive iteration, and so persist subjectively forever in a cooling universe. The mathematics is genuinely arguable. The physics, as far as anyone can tell from here, is not yet decided. But this is what escape looks like, if any escape is possible at all. It is not a rocket leaving Earth. It is a species transforming itself so thoroughly that it bears no physical resemblance to anything you would call human, in service of staying alive in a universe that has stopped being hospitable. You, personally, are not getting out. Neither am I. Let's come back. The Sun is going to swell. Earth is going to be vaporized. None of that is happening on a timescale that should affect what you do tomorrow. What might affect what you do tomorrow is this. The next Carrington-class CME could happen this year, could happen this decade, could happen tonight. The probability per year is roughly between 0.5% and 1%. The probability over your remaining lifetime is significantly higher than you are emotionally prepared to accept. It is, on any reasonable estimate, larger than your lifetime probability of dying in a car accident. The infrastructure that holds your world together, water pumps, food distribution, satellite navigation, internet, refrigeration, communications, the electricity in the wall behind you, was not designed for a Carrington event. The grid was upgraded for a 1989 Quebec scenario, which is somewhere between a 10th and a 50th as severe. In May 2024, we came close. Not close enough to topple the grid, close enough to remind every infrastructure engineer who watches this sort of thing that the next one is rehearsing. Solar cycle 25 is still ramping. The current solar maximum is the strongest in 2 decades. The window is open. The arithmetic does not get more favourable. If you want to do something about the way the Sun is going to end us, this is the death you can actually engage with. Lobby for hardened infrastructure. Vote for engineers and scientists who take this seriously. Keep 2 weeks of food and water in the house. Know where your nearest hospital is. Print out a paper map of your city. Make peace with the people you love. We're not going to outlive the Sun. We're not going to outlive the biosphere. But there is one cosmic threat with a roughly coin flip probability per century that we can engage with directly, by being slightly less dependent on the assumption that nothing very dramatic is going to happen to the star at the centre of our system. Something dramatic is going to happen. 3 things, actually. The first is rehearsing. The second is 1 billion years out and probably solvable by a sufficiently long-lived species. The third is 5 billion years out and unstoppable. You will live through one of them, or you will live through none of them. The Sun does not care which. What you're watching when you look at the Sun is a thermonuclear reactor in the middle of a 10 billion year shift, halfway through. Halfway. It has been burning hydrogen for about 4.6 billion years, and it has about another 5 to 5.4 billion years before the core gives out. Right now is the geological pleasant moment in the middle, when the Sun is the right brightness, the Earth is the right distance, and the silicate weathering thermostat is still in the green. In 1,000 human generations, the green goes. In 40,000, complex life is gone. In 5 billion years, the planet itself is. None of those numbers depend on what you do, what you buy, where you hide, or how rich you are. The atoms in your body came from a star. They will go to a star. Possibly the same one. Possibly a different one, depending on which way the gas drifts after the Sun expels its outer layers. Either way, what you're made of has done this before, and what you're made of will do it again. That is, in the end, the cosmic accounting. You're not durable. The Sun is not durable. The galaxy is not durable. The universe itself is not durable. But you are made of the residue of a previous death, and the people you love are made of it too, and the same atoms that are doing the work of you right now will, in some unimaginable form, be doing the work of something else, somewhere else, 100 billion years from now. Whatever the Sun does to us, The flare next decade, the slow shutdown in 1 billion years, the engulfment in 5. It does to all of us, together, equally, indifferent to anything we built or owned or fought over. We came in together, we go out together. The sun does not negotiate. Thanks for watching.